Okay guys, now we're down to the two really good videos in this section, and that is videos that model exponential growth and decay, specifically radioactive decay, but also population growth. And so we're going to look at decay as an example here, specifically looking at using our continuous growth model in order to, I guess, model decay. And so these are going to be our two big models that we often look at using to represent growth or decay of some initial quantity over time. So let's go ahead and take a look at this problem here. It says radium-226 has a half-life of 1,599 years. And that's going to be important here in this problem to remember that value there, that its half-life is 1,599 years. At least we have to wait that long before our initial amount's cut in half. It says for us to write a model to describe the amount y that will be left after a certain number of years x. And so in terms of write a model, now that's kind of a thing here. Like, what do you mean write a model? What I want you to understand is that when we're representing the growth or decay of something over time, we tend to use our continuous growth model nearly always. Because look at this video we just did over compounding interest. When we use this, that tends to be a really complicated thing. When we assume that something's compounding or decaying infinitely many times within a given period of time, we can just use a base e. And we say that we have this a equals pe to the rt like model. So I'm going to go ahead and write this here. We're going to say that because I want to model this with a simple model that's continuously growing or decaying, we're going to use this model right here. Or in other words, we can say y equals a e to the bx, okay? Where we say that a is the initial amount. And b, in this case, is equal to our rate. And we can certainly see that here where we refer to these other y's as the principal and the rate. So, for part A, we have to write a model to describe the amount y that will be left after a certain number of years x. And so when we say model, I want you to go ahead and write this over here. We say this is our model. In this particular instance, we're going to say the amount at a given time is equal to our initial amount. So we would say that that is our A. E to the Rx or Bx. This is our model here. So when it comes to writing a model, what are the two things we're going to want to need here, or need to have? We need, in terms of a grocery list here, we need the initial amount and we need the rate. And if we don't have these things, these are going to be things that we have to go look for. So with respect to our model right here, we say that on part A, it says use the model to determine how much of an initial quantity of 20 grams of radium-226 that will be left after 2,000 years. Okay. So first things first, let's go ahead and make our table as we are wont to do with these models here. And we're going to say that we have x and y, and these are really indicative of time. And this is in years. Okay, so years. And then we have an amount. And I'm going to go ahead and tell you that this is going to be measured in grams. Okay, so in this first problem here, what we're told is we have an initial quantity of 20 grams. We want to know how much is going to be left after 2,000 years, okay? So I'm going to go ahead and put 2,000 right here. And what I want you to understand is that our model, when we plug this in, is going to look a little bit like this. We're going to say that the amount that we have here is equal to the initial amount, which in this case we were told was 20 grams, e to the b times 2,000, okay? So now the weird thing here is that we kind of have two unknowns. We don't know how much would be left, and at the same time we don't know the rate. So how are we going to figure this out? Like, this is just like a really hard thing. We actually have two unknowns. And so here's where the half-life comes into play. We say half-life of 1599. And so what I know is this. At exactly 1,599 years, at least in this first example here, we're going to be left with half of our initial quantity. And so what that means for us is we can actually say that there would be 10 grams left over of this initial 20 grams. And what that's going to allow us to do is it allows us, let me undo that right there. This part right here allows us to determine the rate. So remember that we need the initial amount and the rate. We already know the initial amount is 20 here. And we want to be able to plug in 2,000 for the time and find this over here, the amount that would be left over. So in order to do this, what we're going to do is we're going to use this data point right here, this 1,599, 10. We're going to plug it into our initial model over here. And we're going to solve backwards for the rate. And so what we know is this. We know that there would be 10 grams of material left over if we started with 20 grams of material, and we said that this is e to the b, or the rate, times the time. In other words, we can say that if 1,599 years have gone by, then this initial 20 grams is going to turn into 10 grams. And so, again, what this allows us to do is solve for the rate. And once we know the rate, we can go back and write a proper model where we know both of our initial quantity, so our initial quantity here and the rate. That would give us a model that we could use to set up and plug in a time and find an amount, or plug in an amount and find a time pretty easily here. So let's go ahead and work on solving for our rate here, which means start by isolating the base of our exponential equations. We're going to divide both sides by 20. And I'm going to leave this as a half. And we get a half equals 1509 e to the 1599 times b. So now that we've isolated the base here, let's go ahead and use our one-to-one property. It's our inverse property really, but it's our one-to-one property that allows us to take the natural log of both sides. And so we have the natural log, let's do this in red here, the natural log of a half on the left, and this is equal to 1,599 times b, which only leaves us with this division of 1,599 in order to give us the rate. And so we have our exact rate is the natural log of a half divided by 1599, so we say our rate is equal to the ln of a half divided by 1599. That's our exact value. And we want to get a decimal for this. So as an advice, a piece of advice, at least with rates here, we want to go out to at least 4 non-zero digits, the first 4 non-zero digits. So as I type in the ln of 1 divided by 2 here, and I divide that by 1,599, I get this. And you know, I see this little e right here, e to the negative 4. So we have negative 4.33, negative 4.33, e to the negative 4, in other words, times 10 to the negative 4. In other words, what we have here is approximately, and if I scooch my decimal back 1, 2, 3, 4, we get negative 0.30, and then a 4, 3, 3. And so you might think, well, that's not very fun. Our rate is that small. And as a matter of fact, these things decay very slowly. And so that is indeed our rate. And so once we've written our initial model up here with our initial quantity, we're going to plug in our half-life and say that our initial quantity decays to half of its initial amount. So we have our rate and we have our initial quantity. And so I'm going to write both of these down here. We say our initial quantity is 20. Our rate, okay, is this percentage right here. We are going to rewrite our model, and in this case, we're going to write it in where we know the initial quantity, 20, or 20 grams. And this is e to the negative 0.000433, and as a matter of fact, I need one more non-zero digit, so 4335. And this is times x. So now that we have written this model, the neat thing here is we can just go ahead and start using our model. So for our first question, we said, okay, well, how much would be left after about 2,000 years? We would say, well, then our model would predict that it would be 20 times e to the negative 0.00043335 times 2,000. I'm going to wrap that up in parentheses here. So let's go ahead and get a value for this. It looks like we would have, let me go ahead and get my calculator rocking, 20 e to the power of negative 0.00043335 times 2,000. We have to end that parenthesis, so it does our exponent first. We get about 8.40, and this is 8.40 grams of material left. And so I'm going to go ahead and put that on my table here. We're going to say 8.40, and one thing that I think is worth mentioning is after more time goes by than its half-life, we would have less than half of its material left, which 8.4 is less than half of its initial material. Now, this was two parts of this problem. It says if there exists 2.8 grams of a quantity of radium-226 left after 2,000 years, how much must there have been in the initial quantity? This is a little bit different. And so what I'm going to do is I'm going to carry this actually over into a new canvas because we're switching the problem around here. We say that we know how much of a material exists. This is our y variable here. We say how much was there in the initial quantity if this much material was left after 2,000 years. Okay, and so we're going to go ahead and let me borrow another canvas here. we're going to set up a new table. We're going to say X and Y. And this time I'm going to say, well, if after 2,000 years there are only 2.8 grams of material left, then how much was the initial quantity here? Okay. So again, with our model, we have Y equals AE to the BX power here. And this time, we're given two other quantities to plug in for our X and our Y. And we're asked about, I guess, what the initial quantity would have been here. So one thing that I'm going to say is, because this is still radium-226, we still have the same rate of decay that we had in the first part of the problem here, which is this guy right here. And so what I'm going to do is, with our model, we're going to say there would be 2.8 grams of material left if we started with some initial amount that we don't yet know. And this is times E to the negative 0.00043335 times, in this case, 2,000 years, okay? So you can see that in this instance, what we're looking for is A here. This would be as easy as then we could divide both sides by E to the negative 0.00043335 times 2,000. And we have to divide on both sides here. We say E to the negative 0.00043335 times 2,000. But these would cancel, and we would get left with just this as being our value of the initial quantity here. So let's go ahead and get our calculators and determine an initial value here. We would say this 2.8 divided by, in parentheses, I suppose I won't have to do that here, we'll just say e to the power of, we have negative 0.00043335 times 2,000 in parentheses. We say that you must have started with 6.66 grams of material. And so that is to say that our initial quantity would have been about 6.66 grams of material if this was radium-226, and if we knew that after 2,000 years we had 2.8 grams of material left. Cheers.